which one? I think you're probably okay. Time control. Yeah, no idea. I think you're okay. I don't see it.
1, 2, 1.
You're on. Do you know how to do the volume control on the lapel? Yeah. Because this thing seems to be tied to the.
So it looks like it's the wrong one.
I think it's this one.
It's this one. It's not. Yeah, it's this one. It's not this one. So it's the
like
wrong.
if you mute it, that does not use this. So I don't know how to switch the different mics.
I mean, then.
Mute microphone, just press this button. Yeah, okay, right. But that's not helpful.
Does this not work?
No.
It is working, but it's not working a lot.
1. Oh yeah. Oh, you're right. Oh, it's working.
Okay.
Oh, okay.
I think you're good. And
Just crank this up. Oh, see, we have to crank this up and mute this one. Maybe that's why it says that. Okay. Well.
Okay, it is 11, but we start at 5 after usually.
Okay, is it going for that?
Hello. 1. Yeah.
You're good.
A little bit.
You're good. I mean, unless you're
Marginal. That's fine. I mean, I have a loud voice anyway.
your voice is good. Good. I'm going to go sit down. But
Let people because we have not like this. Some people are coming from the other side. So we're split. My quota is having faculty. Might get.
No.
Coming back on the perch. So there's a shuttle that takes them back and forth.
Oh, I see. This is a show. I don't even know why this is.
And the camera walk. So it's a nice place for the camera.
Oh, hi, George.
Okay, so let's start. I guess everyone's here already and eagerly waiting for Kilian to give a talk. So it's a great pleasure for me to introduce Kilian Weinberger back to Penn to give a talk. Kilian was a student not too long ago here. In fact, this morning we went to the grass lab and took a picture next to his cubicle. And I hope many of you will come back here on stage in the future. Kilian currently is a professor at Cornell University, where he has done fantastic work on machine learning and crossover sum to computer vision. In fact, Kilian had 2 best papers at CVPR, 2 more than I have. So. Kilian received his undergraduate degree in computer science and mathematics from Oxford University. Kilian is known for many work he's done on dimension reduction, manifold embeddings, and lately Kilian has gotten into the deep learning and really making a tremendous progress in this area. So this is the area I think is going very fast. And a lot of things are still being figured out. Kilian is in the middle of it. And in fact, some of the best work done in this area is coming from Kilian's group, including the densely connected networks and also stochastic shrinking the passage on the network. So a lot of details in the system. In sort of the distance all look the same, but if we dive into it, there's a lot of insight that I think Kilian's drawing from in different areas. So it's a great pleasure to have Kilian back here, and we are looking forward to seeing his talk today.
Thank you very much, Jumbo. It's really fun to be back here. I will be talking about deep networks with dense connectivity. And before I... Oh, is this working? Correct. Apparently it's not. 1 second. Oh, now it works. Okay. Okay, good. So before I get started, I want to give a 3-minute introduction on what deep learning is. So I'm sure a lot of you have heard of deep learning or are doing it, but it's the kind of thing that's so buzzed these days that, you know, I just want to pinpoint, like, what do I mean by deep learning? And, well, to talk about deep learning or to, you know, say what it is, we have to start when 1957, when it was invented by Frank Rosenblatt. And, well, he didn't call it deep learning back then. He called it perceptron. And the perceptron, in some sense, was the first algorithm that had the following idea. Imagine you have data, and in this case, I just have positive and negative data points. They're just points in a high-dimensional space. So you can imagine emails as these are good emails and these are spam emails. Obviously, in 1957, they didn't exist yet, but that's as good as a problem as anything else. And the perceptron, and a lot of you know this algorithm, was the first algorithm that actually finds a hyperplane to separate the positive points from the negative points in the space if such a hyperplane exists. So that's provable guarantees. And once you find that hyperplane, then for a new test point, all you need to do is you just say, okay, well, if I have a new point here, I want to know is that email spam or is it not spam? I just look which side am I on. And if I'm on the spammy side, then I would say it's spam. Otherwise, I say it's not spam. And so that check is just an inner product. So you just have this new point x. You just compute the inner product with w. This is very basic. We can draw this as a very simple neural network, just using this kind of graph where you basically say this is my input, and I connect these to the output, and this basically means I'm summing over these, and here I'm saying I'm multiplying this value with this value. So this is just the way neural networks are drawn. It's just to avoid equations in talks, because people don't like those. Okay, then, well, this was great, and actually back then, the articles, media went crazy. It's really fun to look at old articles, actually, from 1957, where people actually ask, like, this is basically a neuron, and very soon we will have brains, and they will, there will be armies, and they will, we will talk to them, etc. Some of it became true, 60 years later. But back then, it was obvious that this is very limited, right? So you just basically have a hyperplane, and what if, for example, some red point would lie over here, right? Then you couldn't actually separate this anymore. And for the perceptron, there's no guarantee what you get in this case. So he extended it and came up with the multilayer perceptron, and the idea was very simple. You just have a linear transformation of your inputs. You just have x times w, and then you have some nonlinear function. And what typically people nowadays use, he didn't use that back then, but nowadays you just take a max with 0. So you just say, if it's negative, just set it to 0, right? That's good enough. So you take your input, you have a linear transformation, so you stretch it in some directions, right? You shrink it in others. Then you set all the negative values to 0, and then you have a hyperplane. That actually gives you rise to some nonlinear functions now. Okay, so this is now 1961, and then machine learning has been occupied for decades trying to make these kind of algorithms more powerful. Right, this is kind of the most basic machine learning algorithm. And well, there's two different approaches, and for a long time, one approach was the dominant approach, and that was, well, if I want to make this more powerful, one thing I can do is I can increase the number of nodes here. So I can actually make this here basically a transformation that maps into a higher dimensional space. In a higher dimensional space, there's more ways to place that hyperplane, so I get a more powerful classifier. And if you know support vector machines, that's essentially what that does. So in support vector machines even map these into an infinite dimensional space. That seems like a very good idea, and it's what everybody did for a long time. There is another way of making these multilayer perceptrons more powerful, and that is, instead of making them wider, so making them deeper. So what we mean by this is we actually, instead of having just a single transformation, we take your x and multiply it by a matrix. You take the output and multiply it again by a matrix, and multiply it again by a matrix, and multiply it again by a matrix. Right? That was considered a really bad idea for a long time, for two reasons. One is theoretical and one is practical. The practical reason is that matrix vector multiplications are very slow, or used to be very slow, so it would take a long time to train that thing. The second thing was that theoretical was that you could prove that actually there's nothing you can learn with such a thing that you couldn't learn with a single hidden layer neural network that's very wide. So it was unnecessary, or it was considered unnecessary, and it was considered very slow. So there's no good reason to do it. But things have changed. And one interesting thing happened is that young kids, if you're PhD students, it's kind of when you were kids, they did something different. These kids didn't play outside anymore. They played inside. They played computer games all the time. And used, that gave rise to GPUs, or made it lucrative for NVIDIA to develop GPUs and sell those. And using these GPUs made matrix vector multiplications really, really fast. Right? So suddenly this wasn't slow anymore. Suddenly it was fast. So thank you. And the second thing, well, the theoretical result that actually you can learn anything with a single, hidden layer, well, that's kind of, as theory goes, right? It's, asymptotic, and there's actually, exponential factor there. So for finite data, actually, that's not quite true. Right? So as you all know, deep learning really works, particularly on images. So there have been amazing breakthroughs in the last couple of years, and things where, a lot of people said, well, this is, this problem X, for example, object recognition, getting that to a human level, right? People thought that maybe 50 years away, suddenly happened, right? And at the bottom, or Siri, right, speech recognition, right? Suddenly, speech recognition was good enough that we could build things like Siri, etc. So this really came down to basically being able to train these deep neural networks. Okay, so deep learning is really, really cool. So what I want to kind of examine is, well, can we somehow improve it? Like, is the way we do it, is this the right way? Or, because this, it was invented in 1957, right? Have things changed since then? And, well, let's take a look at a modern neural network. So this here is in the model neural network. You have an image that comes in. So you have some convolution operators. So it's not exactly multiply. It's a little bit different. But it's essentially the same thing. And at the end comes an output. So you have many, 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 many layers. Right? It's very, very deep. You take the input. You process it until you get your output here. And essentially, it's very similar to what Rosenblatt invented in 1961 with the multilayer perceptron, except, however, having just a few layers, we actually now have many. And well, that's actually a significant difference. So when you think about it, right, that reminds me of a game that I used to play. You guys don't know it because you play computer games. But here's the game. It's called Telephone. And the way it works is someone sees an input, and then, sees an input. Someone has some idea. And then you basically whisper it into the next person's ear, and then you whisper the next person's ear, and so on. And the last person screams out what it is. Right? So that's the game. Do people know this game? It's called also Chinese something. I don't know. And so in this case, for example, the person sees a car, so you say car, and car, and car, and car, and car, and the output is car, right? So in this case, the analogy here is every single layer basically speaks exactly to the layer after it, and at the end you have the output. Now, well, there's a reason why this game is considered to be fun. And why is that? Well, because people mess up, right? So what happens is, when you usually play it, right, at some point someone says something wrong, or here's something wrong, in this case this girl here, here's the wrong word, and then she passes that on, and at the end you get kind of the, a mistake. And that happens, that it's more likely to happen when you play with a lot of people, right, because someone is likely to mess up. Well, that's exactly what happens in deep neural networks, right? So now we are playing this game of telephone, right? We have many, 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 many layers, way more than Rosenblatt would have probably thought is ever possible. And a single layer, right, can mess up and then mess up everything else afterwards, right? And the problem is that's more likely, as these networks get better, deeper and deeper, that's more likely to happen, right? And the worst thing is you can't detect it. Why can't you detect it? Because this layer doesn't mess up during training time, right? If you mess up during training time, so then you just knock it over the head with your stochastic gradient descent and you fix it, right? And you fix it until it gets it right. It messes up during test time, right? When it sees a slightly different car, for example, than what it saw before. And now basically it fails to extract some features that are necessary later on to extract some other features, and it propagates down, and before you notice it, you misclassify. The good news is, and this is what this talk is about, is we can mitigate it. And the way we will do it is we will reduce the impact of a certain layer. Right? The problem is basically you have this chain where every single layer is a bottleneck. So if we can somehow fix that and avoid each layer being a bottleneck, then we can maybe get around this. And actually there's some other work that's very, very influential that actually does that. I'm not sure if they intended to do it, but that's what they're doing. It's called residual networks. So that's a very, has a huge impact. It was actually only 2016, but I guess at this point, they won the ImageNet competition and made a huge splash. And they had a very simple idea. They said, okay, well, we have this neural network, and what we do is we divide it up in blocks, and then we have these connections where we say the input to this block is not just the output of this block, but it's the output of this block plus the output of this block. So we take the signal here that goes through here. We also kind of let it go around here. Right? And so what happens now if this guy messes up? Well, you have some kind of bypass, some security path where the information can flow. That's great, and that actually really made a huge difference. Right? But it didn't really address the problem heads-on. And in particular, during training, actually, these never really mess up, right? So these are still very, very good, and it's somewhat this is a good fix, but it's too weak. So let me explain you a very, very simple fix. That's more drastic. So if you now pay attention for the next minute, you get it. It's really simple. So here's what we do. We say this is our neural network. And we know during training, all these different layers work really well. Right? During testing, some of them are going to mess up. Right? So what we do is we just simulate that during training. And here's what we do. We just introduce a coin for every single layer. And when we have a mini batch that goes through, we flip a coin for each one of these blocks. And if it heads, we say it's good. And if it tails, we say this one now messes up. And we simulate the most drastic way of messing up. We just remove it entirely. So we remove the entire block and basically pretend they never existed. So now they actually get a much, much shorter network. And now you do a forward pass. You compute the loss, and you do a gradient pass backwards, and you update your weights. So you just pretended that the whole network was just this much shorter network. Then you go to the next mini batch. You again take out a coin for each one of these blocks. You toss it again, and you remove some different layers. So that's all there is to it. One little detail, you don't actually remove everything with the same probability. In part, if you remove the input, right, there's nothing left anymore. So you don't want to do that. Right? So basically what you say is, well, you never remove the input. And you remove the output, the last layer, sorry, not the output, the last layer, with probability p, which we just set to 0.5. And we interpolate between those two. Right? So this here is less likely to be removed. This is more likely to be removed. That's all. So you just still have one parameter as the probability of removing the last layer. Okay. And so here's basically one more time. Here's what you do. You just go through, you always take a mini batch. You take a bunch of images. You remove a bunch of layers. You do a gradient pass. You take another mini batch, remove some other layers, and so on. You just go through your data set over and over again until you're done. And during testing, you just take the whole network. One little detail. When we take it during testing, we do a little correction, bias correction. So what we do is we weigh every block by the probability of it surviving. Right? This is just correcting for the fact that it wasn't there all the time during training. Okay. So similar to people familiar with dropout, one immediate thing you realize is that the network that we use during testing is a network that we actually never saw during training. We only saw bits and pieces. Right? So what we did during training is we always removed some of them. So in fact, if you have L layers, there's 2 to the L possible networks that we kind of trained simultaneously, and we kind of take a weighted average of those during testing. So that's some kind of ensembling effect. There's another thing going on that's very important, that during training, the network is a lot shorter than during testing. And that has 2 very important effects. The first one is that information flows much better. So if you have a shorter network, right, so imagine, for example, right after initialization, these are all random operators, right? So you take your image and you apply random filters on it, right? At the end, very soon, there's little signal left. The same with the gradient, right? You propagate the gradient back. If you have a very deep network and you keep propagating back, right? You keep multiplying with matrices, right? Typically, there's a problem that the gradient vanishes and washes out, etc. That's improved if the network is shorter. There's another advantage. If the network is shorter, it just becomes faster, right? Significantly faster. So you have better information flow, and it becomes faster. The question is, does it actually do anything? So, yeah.
Can you actually say it's faster for training? I mean, each evaluation will be 25% faster.
Yeah.
But you might reach your local minima slower.
Oh, I see. No, it is faster. Yeah, it is faster. Yeah, good question. So his question was the following. Yes, each forward and backward pass is faster, but it may take a lot longer to train, right? But yes, it is actually. Turns out it's faster. Okay, so how well does it work? So here are some baselines. The first thing I compare against is ResNet. So ResNet actually is basically a deep net where we have these connections. That's the network I just told you about. And these are three methods that actually address somewhat similar problems. These are basically methods that came out recently to address kind of the problems people have with training these very deep neural networks. So one is ResNets. Another one is batch normalization. Batch normalization, what you do is you take the inputs and you just zero mean them and divide them by the variance, just that they are kind of, standard deviation 1. Right? You learn that too. But again, that helps a lot with deep networks. And there's dropout. Dropout actually is very similar to what we're doing and wasn't essentially an inspiration. But instead of making it shorter, it makes it less wide. Right? So you remove nodes kind of, in the other direction. The state of the art, when we submitted the paper, published the paper, was actually, on ImageNet, was a ResNet with batch norm. So dropout, turns out, doesn't help much if you use batch norm. So that's what we compared against. So basically what we did is we took the state of the art at the time, which was this, we took exactly the same network with exactly the same hyperparameters. We got it from the authors, same code. We could reproduce exactly their results. We took 3 data sets, Cypher10, Cypher100, and SVHN. Cypher, these two are images of, tiny images of, in this case, 10 different classes, in this case, 100 different classes. And basically, given the image, the task is to identify what class does it belong to. So a class could be aeroplane, could be car, could be house, or something like this. SVHN stands for Street View House Numbers. It comes from Google. When they ran their Street View car, they want to recognize house numbers. And basically, those numbers that they had trouble recognizing with, they collected those, made a data set out of it, and said, here, test your algorithms on it, how good it gets at recognizing these numbers. Okay, so on all of these data sets, this here was the previous state of the art. That was basically the ResNet and with batch norm. And just to see, ultimately our goal was not to be the state of the art. We just want to know what's the effect of our method. So we took exactly the setup of the previous state of the art, and the only change we made, we didn't change any other hyperparameters. The only change we made is that we introduced the stochastic depth. So basically that we dropped these layers, and we used a probability of 0.5, just because it's easy. So if you do this for these 3 data sets, that's what we get, right? So for every single one of them, there's a massive drop in error, right? And so I'm saying massive because this is really huge, right? Like people are really fighting over these every single percent point on these data sets, right? And the cool thing is, like we made the training actually a lot faster, right? So we made it faster, and the error went down. So we were really excited about this. And basically what it showed that we could, it basically helps mitigating some of the problems that you get because these networks are so deep. So my students, they were like, wow, maybe you can learn even deeper networks, right? So 110 layers seemed ridiculous at the time, right? They were like, now we can train really deep networks. So they went to 1,200 layers, right? Let's go all in, right? Use the electricity of a small town or something. And yes, the error went further down, right? It went from 5.3 to 4.9, right? And that was the first time that anyone could train such a ridiculously deep network and not overfit. Right? Usually if you could do this, but the error would go up, right? You would actually do more harm than good. This was the first time that this was possible, that actually error still went down. And just to visualize this here is 1,202 layers. So my students were super ecstatic, right? So this was already the new record on this data set. They got even better results, 4.9 results. They were like, awesome, we got the world record on this. Right? They were really happy. And I was happy for an hour. And then I kind of had this weird feeling in my stomach. It's like I've just done something terrible, right? And I went to my students and was like, I'm not feeling good about this. And they're like, this is awesome. It's like, no, right? People are going to do this. People are going to train 1,200 layers, right? It's going to use enormous amount of electricity. It's going to pump CO2 into the air. I feel responsible for this. Right? Just for a few percent point. Like somehow we told the world to do this, and I don't feel good about it. So, okay, we have to say, we have to, before this gets out of hand, we have to think about, do we really need this, right? And in fact, we've actually shown, right, that we don't need that many layers. Right? So something is wrong about this setting. And let me just explain this, right? So here's why it's so deeply troubling. Think about each layer in your network as basically a kind of a little program or something, right? That reads in the output of the previous layer, then does some modification, and passes on to the next layer, right? So you basically have this, this is the telephone game, right? So you read something in, do a little modification, pass it on. What we showed is that if you take one of these layers and you just remove it, nothing happens, right? Well, it couldn't have done very much, right? Like, if you have, imagine you have a construction site and, some of your workers get hit by a bus. It's like, oh, it doesn't matter. They didn't do anything anyway, right? It's not a good thing, right? So somehow, none of the layers can be very important. Right? And we also tested this. During test time, you also dropped out layers, and it worked fine, right? So basically what we've shown is, that actually these neural networks have an enormous amount of redundancy, right? Probably the majority of the parameters don't do anything, right? And by forcing it, basically, to live with these dropping layers, we just surfaced that problem. So let me give you another perspective why it helps, though, right? So why is this, we have all this redundancy, but why did dropping these layers help? And let me give you a totally different explanation. And that's the following. That basically, what we do is, we drop these layers randomly. So imagine we drop this layer here. Before this layer here was connected to this, I call it blocks, but whatever. Like this block was connected to this block. If I drop it, then it's suddenly connected to this layer here, right? With some probability. So I have some probability that it's dropped, right? And if basically this one is dropped, but this one is not dropped, and this one is not dropped, then you have a direct connection between these two, right? And you can write out these probabilities on top of this. Okay? So you basically get these kind of connections between different layers. And that's when we realized, wait a second, right? We didn't actually solve the problem that we went out to solve. Right? We're still playing bloody telephone. Right? The only thing that we're doing is we just remove people. Right? So this guy now has to speak a little louder, right? So that this guy hears him, even if this girl in the middle disappears magically, right? But that's not a great fix to our problem. There's a reason why when we have faculty meetings, right, we don't all sit in a row and talk to each other through telephone, right? Because it's incredibly inefficient, right? At least not, in our department. Maybe some departments. What we do is we have this setup, right? Where everybody can talk to everybody else, right? And there's no bottleneck at all. So why don't we just fix the problem at the root? And that's what we then call dense connectivity. And so the idea is very simple. We have our network, and what we do is, instead of having a connection from each layer to every other layer, we basically have connections from every, instead of having connection from every layer to the subsequent layer, we have a connection from every layer to every layer that follows afterwards. And the nice thing is now, kind of this, in some sense, like ResNet's kind of on steroids, right? So if any one of these layers drops out, well, it doesn't actually matter, right? Like you have the connections directly here, right? And you have information flow. If you take the gradient, it flows directly over here, directly to the first layer, right? So if a network is really, really long, gradients don't vanish. It's not a problem. Now, some people thinking, wait a second, right? This is crazy. Why is this crazy? This can't work. Because what do we do? Well, each one of these layers, each of these arrows actually has parameters attached to them, right? These are actually weights, right? So if you take all these inputs, each one of these basically means this guy now has all these inputs, and we have to learn parameters for all these inputs. So what's happening is beforehand, the number of parameters of the neural network was linear with the number of layers, and that was already a lot, right? These neural networks now have billions of parameters. Now we made it quadratic. Right? So that can't work. Well, it can. And the trick is the following. Before in neural networks, normal neural networks have pretty wide layers here. Right? And people just, empirically realize that's important. You need to have really wide layers. Right? Otherwise, it doesn't learn much. Turns out the reason you need these really wide layers is actually, this redundancy problem. It's actually basically what happens, you extract some features here, and what people thought is, this is the input, the output here, the input to this layer, and that basically now learns some, here you learn some low-level features, like, for example, edges and so on, then you learn some more high-level stuff, and so on, right? But that's actually not really what's happening. It's true that you learn low-level stuff here and high-level stuff here, but you still need the low-level input at these later layers. And how do you get the information from these earlier layers to the later layers? By just copying it over. So most of what the neural network is doing is just copy stuff over and over again. Right? We don't need to do this because we have a direct connection here. So we can make this really, really, really thin. Right? Our network now has a width of 12 channels or something, or maybe even less. We call this the growth rate. Right? So we just have, because of this, actually, these dense networks use actually a lot fewer parameters than ResNets, for example. And another way of looking at this is that basically each layer, what you're basically doing is everyone afterwards has access to every single feature that was produced. So all a layer does is just adds the features that basically didn't exist before, right? There's no point in creating any feature that already exists, right? Because anyone can access this, right? Whereas before in the old architecture, if a feature was good, you have to recreate it, right? You have to pass it on, right? And you're wasting a lot of energy, a lot of parameters that way. So how do you implement this? There's a really trivial implementation of this. You can just basically reduce this to a traditional network by saying, okay, I have my input, I transform it to get my first output of my first layer. These are my first activations here. And now I just concatenate my input, and I compute the next layer. And all I'm ever doing is just concatenate the layer, right? So this concatenation basically implies these long distance connections. So if you implement this as one line of code, that's an inefficient implementation. You couldn't make it more efficient if you don't copy any memory. And we made that open source, etc. But just want to play with it, it's very, very simple. Okay, just truth be told, there's one more detail. You can actually only connect layers that have the same size. Like if the features have to have the same size. Otherwise, it gets tricky. So, but you usually have these pooling operators where you actually take images and you shrink them. So what we do is we connect everything with everything until basically the size shrinks, and then we connect everything with everything, and so on. But it looks like these pooling layers are now bottlenecks, but they're not really, because actually the input here is actually every single feature that was computed here. So these are kind of the widest layers in the network, right? So they're bottlenecks, but they're really wide. So no problem. Okay, any questions about the setup? Okay. So the question, how well does it work? Well, again, same data set. So we took Cypher 10, Cypher 100, and we did ImageNet. So ImageNet is a data set that has 1,000 classes, 1.2 million images, and for each image you have to say which one of these classes does it belong to. We didn't use this before because you need a lot of GPUs to train on this. But then we got access to these GPUs, so we could try that too. One thing I didn't mention before, we just use standard data augmentation. So for those people who know this, for every image, basically we just randomly flip it or something. This is what everybody does to increase the training data set size. Okay, so here's the results that we had before. This is Cypher 10, this is Cypher 100. This was the ResNet. This was if we just introduced stochastic depth. And this is when you're into this 1,200 ludicrous long neural network. And if we now take a 100-layer dense net, bam, right? We beat that one. And the crazy thing is, right, we only use 8% of the parameters. So we go from 10 million parameters to 0.8. Right? So we have a 92% reduction in parameters. Right? So I was like, awesome, okay, good, right? So now, we're not going to destroy the world, everything is good. And my students were like, awesome, now we can make really big dense nets. And they made the mother of all dense nets, 26 million parameters. And they got 3.5 error rate. So they beat their own record. And now we have the same problem as before. But then, okay. So I still feel guilty. But you can actually now make very small networks that are very, very competitive. And if you want really the amazing thing is that this actually, because actually more compact, you can actually still squeeze them on GPUs. We also tried on ImageNet. ImageNet is a highly contested data set. ResNet was the previous winner. And what I show you here is the error, so lower is better on the left-hand side, and the number of parameters here on the right. So in some sense, it's hard to compare different neural networks. So what we do is we kind of do it as a function of the number of parameters. So if you train a bigger network, typically it does better on ImageNet because it's a very large data set, so more parameters help. And what you see very, very clearly here is that for the same number of parameters, right, there's a significant gap, right? So DenseNet outperforms ResNet by quite a bit, right, for the same number of parameters. And if you want the same accuracy, right, you get a significantly smaller network. So for example, if you would say, I want to have this accuracy level, right, then actually instead of, whatever, 18 or 16 gigaflops, you just need 10 gigaflops. Sorry, this is the number of parameters. This is the amount of electricity, I guess, ultimately, you need during test time. Any questions about this part? Yeah, Lion.
Yeah, awesome. So could you say a word of the highway networks or longer range connections, how this fits in or doesn't fit in? You're actually doing block deep connections and you're not actually doing anything that spans the whole length.
So I guess highway networks, they are similar to the first part, the stochastic depth, right? Where they basically say but you have a gating unit that actually says, do you want to use this or not? Yeah. What we found is that you just don't need that. Essentially, if you just drop it randomly, that's actually more effective. So you just learn a lot of parameters to don't do much. Okay. I guess other network architectures, I don't know if there's other ones. So highway networks, I guess they're the most similar ones. Those and ResNets, I guess, right? So, yeah. Any other questions? Okay, good. So then, let me move to the last part of the talk. And so, this is actually a little different. It's a kind of a side project, and it's a little bit kind of more food for thought. But what I asked myself is, well, so, I told you deep learning is awesome. Works really well. Works really well on images, by the way. It's not the answer to everything. Some students seem to forget this. Like, deep learning is great for images, and it's also pretty good for speech. Then it works pretty well for text, but it's not actually in every single data set it works so well. So I thought that's curious, and I thought, like, well, why does it work so darn well for images? And so, when I was at Penn 10 years ago, one thing I worked on a lot was image manifolds and manifold learning. And so I thought, well, maybe one reason why deep nets work so well on images is because images lie on a manifold, approximately on a manifold. Or actually, it's really a family of manifolds. So for example, here you have images of men with or without beards. And they're kind of, if you would just take any kind of image, like, these are, I don't know how many pixels these are. It's 300 by 300 pixels. If you would just randomly assign colors to these pixels, you get a point in that space, but that's almost certainly not an image. Right? It's not a natural image, it's garbage. In fact, you could sample your whole life, randomly pick pixels, configurations. You would never get a natural image. Right? So somehow these images lie on this very, very small sub-manifold. Why do I think it's sub-manifold? Well, it's not in subspace, because if I take two images that are far away from each other, for example, this guy and this guy, interpolate between them, I wouldn't get a natural image, so it's not a linear space. Is it locally linear? Well, there's some people believe that, So if you take two very, very similar images, you average them, you still get something that it's pretty close to an image. And so there's a manifold hypothesis that doesn't come from me, that basically says, well, maybe these deep nets learn manifold. So let me explain what I mean by this. Is, well, we have some deep net here. So here comes the input. I stick in some images. And maybe internally, right, the representation inside of the deep net, it kind of somehow managed to flatten that manifold. And why do I believe this? Is because, well, there's a few indications towards this. At the end, the classifier is typically just a linear classifier. So if I have a pretty complicated problem, for example, in this case, do men have beard or not beards? Right? That's very easy for a deep net to classify with a linear classifier. But actually, on the manifold, there's no reason to believe that the bearded people lie in one corner and the non-bearded people in another corner. Right? So basically, what the deep net really does is it embeds this in some space, these images, and then it learns some hyperplane where basically the bearded people are on one side and the non-bearded people are on the other side. And so now we can do a test, right? So you can say, well, if that, there could be many different reasons why this works, but if they actually approximate the manifold, then I could, then I could do the following test. I could take an image that it definitely wasn't trained on. Right? So here's an image of myself. Okay, so I know this wasn't in the training set. I don't have a beard, so I should be on this side of the manifold. Sorry, of the hyperplane. And if the space is linear, right? If I were now to move the image in this direction, I should get a beard. Right? So let's see if this works. All right, so here's what we do. We take the VGG network. So this, this was kind of in parallel to building our own architectures. So we just used, and in some sense, we also want to make a case that this is really not something about the networks we are designing. It's just a generic network. So this is a network that was from the Andrew Zisserman's group from University of Oxford, and they trained this on ImageNet. They put it online. You can download it. Right? So we did not train this network. It was trained on ImageNet. Just take it off the shelf. Now we take this image of me, and we stick it in this network. This becomes a lot of values internally, right? You get a lot of activations in this network. So I just take them all and concatenate them, right? So I get a vector, right? That vector is this point, right? Which represents my image, okay? Now I want to move it. I have to know which direction to move it to. So here's what I do. I just take people that are also men with beards. So here's some people with beards. And here's some people without beards. So I take two sets of images. And what I do is I just find them by nearest neighbors. I just find people that are somewhat similar to me. Right? So, these are all, like, I feel like I look a lot like Ryan Gosling. So. And so here's what I do. I take these bearded men, and I just average them. And I take the same thing with these guys. So by the way, just, to be important, I don't average them as images. I stick them on the neural networks. For each one of these images, I get a very high dimensional vector. Right? So now I get I took 50 nearest neighbors, I think. So I take 50 bearded points, 50 non-bearded points. I average them, so I get two centers. Right? This is the bearded center, the non-bearded center. I subtract them, that gives me a direction, and this is the direction of beardedness. Right? So now if I move myself along that direction, I should get a beard. Right? So the idea is basically I take my point here, I move it in the same direction, and I should get a beard. Here we go. Okay, not convinced. All right, so now we can take this point and reconstruct the original image. So how do we do that? Well, this point here is really just a bunch of numbers that correspond to activations in the neural network. So I can populate the neural networks with these numbers. And then I can just do gradient descent in image space. I can just say, okay, well, here I take an image, just start with some random noise, and then I just do gradient descent, not changing the weights of the neural network, changing the pixels of the image to basically say that, to minimize that if I take that image and stick it to the neural network, I should get exactly this point back. Okay, this is just a gradient descent problem. And this is what I can do. You ready? All right, 1, 2, go. All right, here we go. That's actually the image that we get. There's actually nothing, so there's nothing special about me. Right? So we just took random images of the web. So this is a celebrity data set. These are 4 random people. This is Berlusconi. I guess this is Ralf Schumacher. I don't know these. And so we can, just do the same procedure, and they all get beards. But there's actually nothing special about beards, right? So we can also make them older. We can make their mouth open. We can open their eyes, make them smile, give them spectacles, etc. Right? And so, for example, when we, open their eyes, we just took, 50 images of people that are kind of similar, that are open eyes, 50 people of people that are similar that have closed eyes, and we just got that vector and added it. We can also take images and project them back onto this space, on this manifold space. So here we took images, we just removed the face, and then we project it back. This is what we get. So here, for example, this image here, it basically fills in this face here. This is not the right face, right? This is a face that it hallucinates, right? This is someone else. This person doesn't exist, but it's basically, it reconstructed some face, right? So here you can also see. I don't know who these people are, but, we can also do it in high res. So here, by the way, just to be clear, we did just some filters afterwards to make it look better. So here's this person. This is a high res picture. We just found that it's a random picture. We stuck it in, and now what I can show you is I can show you a movie as I take this person and move it along that beardedness direction and back, right? So here's what happens, right? It basically grows a beard and it goes away, right? Grows a beard and it goes away, right? So here's also, of course, my students have a lot of fun, right, with my pictures. So they did a lot of other stuff. Like when I come in the lab, it's like suddenly they're standing in front of the monitor. It's like, oh, It's like, do you know what you look like as a woman? It's like, I don't want. So there's a lot of images I can't show. But so here's like 2 other random images. They of course also made me look older. So this is what I look like, if I age apparently. They also made me look younger, actually. They actually went to my wife and asked her, is that what he looked like 10 years ago? And she's like, yeah, well, kind of. So here's actually 2 people that this is the original image. We made it look younger, and we made it look older, right? And again, the cool thing here is that it's really just a linear interpolation, right, in this space. So we didn't train any neural network. We did nothing, right? We just took that image, just moved it in that space. That's it. Here's also, my favorite one. This is a little boy, right? And we give him a beard, yes. There's also failure cases, so it doesn't always work. And so here's some cases where it went wrong. And so it's interesting to look at these. So this is a person here that, we added a beard to him. And if you look closely, I don't know if the projector that comes out, this guy's Caucasian, but this person here is probably more African American, right? So basically it seemed to have changed race, right? And what happened there was basically, once we looked into it, it made a lot of sense. Basically, when we took the people that actually had a beard, and we took the nearest neighbors, actually it turns out that, I guess this look, having a beard and I guess being bald, I don't know, seems to be more common in the African American community. So we had more African American people on the target side and on the source side. And so we basically changed 2 things, right? We added a beard and we changed the race. Also, what we found actually that it works a lot worse on women. And we thought about this, and it's pretty clear what's happening is the one thing is women have a lot more degrees of freedom. So, there's a lot more, they have a lot more ways that they change their hair. It actually turns out it's more the other way around. Like guys it's only a couple ways they differ, right? They all kind of look the same. Whereas women actually have different hair, have makeup, etc., right, and have jewelry, etc. So you would need. It just means the manifold is more complex, and you need more data. But it turns out actually that we got less data because our data was actually that we grabbed was actually mostly politicians. So that was highly biased towards men actually. So we had less data, but we would have needed more. So that's why. So here we tried to make her smile, and you just get a strange smile. All right. So just to sum up my talk. I talked about a couple of things. So the first thing is basically stochastic depth. Basically, when you train really, really deep networks, right? If you just drop some of the layers, that makes it a lot more robust, and it makes it faster. And it lowers your test error. So that's a great thing to do, but you shouldn't do it. Why not? Because you should instead use dense nets, which is even better. And then we investigated a little bit, why do deep nets work so well on image? And one reason could be, also, this is not even close to approved. There's just some indication that there could be something that they basically linearize the manifold locally. Here's code. So for our dense nets, actually a lot of people implemented dense nets. So these are actually all from other people. This is our implementation here, which is very memory efficient. And I want to thank my coworkers who helped me on the various projects. Because they were so good, I can give them all a beard. Here we go. So, especially Kavita looks great with a beard here. All right, thank you.
Big talk, yeah. So we have quite a bit of time for questions.
That was a great talk. Thank you.
Thanks.
Did you have classifiers for things like beardedness?
Yes, yes.
So why do this nearest neighbor approach instead of just kind of walk?
Very good question. So he's saying, well, if you train a classifier, you get a hyperplane. Why don't you just go orthogonal to that hyperplane instead of the nearest neighbor thing? The problem is you're in high dimensional space. So if you're just off by a little bit, you totally miss your target. So if you basically take the averages, you're just much more. It's kind of like shooting at the moon, right? Like distances are pretty far in high dimensional space. Like even points that are close are pretty far away. And so it's actually like finding, the orthogonal to the hyperplane, it seems to kind of shoot a little bit away from kind of leave the space, I guess, right, of the images. So if you actually instead take the mean, then you know the target will lie in the space of valid images. So it's close, but in some sense you have to guarantee, you have to be super, super precise, right? And the hyperplanes are not that precise. Right? Yeah, Sean.
What is your criterion for stopping when you drop and drop and drop?
When I drop the layers randomly?
Right?
At the beginning, like when we drop the layers?
Yeah.
So how long do we train? We just do what everybody else does. We just train for 500 iterations over the data set. And then we lower the learning rate, we do another 200 or something. Basically, actually, what we did in these experiments, we used exactly the same schedule as the authors that we compared against, just to remove any degree of freedom that could also explain the results.
What you call manifold, you call it in a really loose sense, in the sense that it's a kind of a discrete, there's really no chart or anything there. I mean, it's kind of a loose way of using it, which is okay, but...
Oh, the manifold, you mean?
Well, it's more like a combinatorial kind of thing, right?
But were you talking about the last part or the...
The last part, yes. Well, you use the word manifold.
Oh, yeah. So okay, I agree. So right, I agree. I totally agree. And I apologize to everyone working on Riemannian manifolds. There's a lot more to this. There's a lot of mathematical rigor that I did not...
Topological manifolds?
So I use it in the way that manifold learning literature does it in machine learning, which is a horrible way of abusing that word. It's very loose. That's right. It's a kind of a fluffy thing, right? It's a loose intuition of what the data looks like. I agree. Yeah.
Yeah, I like the manifold intuition. It almost has to be true. I guess, have you thought about places outside? So certainly images have that property. Language, text, other. I mean, is this sort of tautologically? This may be too hard to answer. True of anything for which machine learning works, or is there really something that makes images quite different, and we should be, in some sense, discouraged from using deep learning but it works for machine translation?
Yeah, so I think that's a good question. So I think for machine learning to work, you have to have some structure, I guess, right? And so one such structure is a manifold. In whatever loose way I mean it. But you could also have clusters or something, right? You could have very different structure. And so, for example, I don't think, for languages, I think it's quite a stretch, I think. And which may also be why deep learning doesn't work so well, right? So that's somewhat consistent with that intuition. But I'm far from any, we're all just trying to understand why is it that deep learning works so well on images, and where does it come from? What are the properties? And so that's in some sense one hypothesis. Yeah.
Question about the first part. So why did you randomly drop things when you do the testing?
Oh, so we didn't actually do it during testing. So we just also did that just to see that it's actually robust against this, which is not surprising because we trained it that way. But actually during testing, you keep all the layers. And you just reweigh them. You weigh them by the probability of them actually being there during training. So that's the idea.
Do you optimize the probabilities in any way?
So you can. So initially we just did 0.5, just because we want to keep it simple. If you vary this, you basically see some curve of, ultimately what you get is a trade-off between speed up and accuracy. You can fine-tune it and you get additional gains. The problem is these deep nets take a long time to train. So it's not if you really want the best accuracy, it absolutely makes sense to tune this. Absolutely. Yeah.
Well, fantastic argument, Kilian.
Thanks.
I'm just wondering if I think about this right way. I mean, if this manifold hypothesis is correct, should it also be the case that if you did the same sort of thing, pull all of the interior weights off and then did straight PCA on that there should be something that is effectively learned?
Right. That's actually what we did initially. So we started out doing PCA. Turns out that we spent almost all our time just doing computing PCA in this high-dimensional space. So then we just removed that step essentially. But that's exactly where we came from initially. So we just and so ultimately you do learn some subspace. The subspace is still very high-dimensional, right? You're still in the thousands of dimensions. So it's not that this is a 20-dimensional space or something, but it goes down from hundreds of thousands or something, right? Ultimately, we realize you don't need it, I guess, right? If you just move in that space. So I guess that's the kind of the answer also to your question. If you move towards the mean, then you kind of stay in that space. So we didn't have to Just to get these images, we didn't have to do it, right?
No,
But to analyze it further, that's certainly interesting. I agree.
Yeah, that's what I mean. If it does lead to effectively, finding the bottleneck in there that actually is the computational implications could be.
Yeah, no, I totally agree. That's right. And there is something to this, absolutely. Yeah.
So you made a case about, propagating information in a feed-forward way, the dense connectivity. I mean, does it make sense to go in a feedback way, or is that? I mean, I'm not in there.
Oh, I see. Okay. So the question is basically, instead of having, so go in circles in these neural networks. Right. So people have tried this, I guess, many times over since the early days of the neural networks. Ultimately, it becomes very messy, and so the problem is you diverge and you get problems. The nice thing about these feed-forward networks, they have certain, they tend to converge very nicely, and
So the training is the problem.
that's right. Yeah.
So in your dense connection network, it's actually quite different from ResNet in the sense that ResNet has a lot of bypass layers, right? So there's a path which you didn't do anything, and you just forward the information.
That's a very good point. That's right. I didn't make that clear, actually. That's right. So good point. So what Jumbo was saying, I don't know how I can go. I don't know how this works. Okay, here we go. Right. Yeah. So in ResNets, you have these connections, but these actually have no weights. These are just identity functions. You just add them on. Whereas we actually learn weights to those, right? And that's right. That's an important difference.
So as a result, would you think so there's an alternative to ResNet, which is FractalNet,
Right.
Which it's quite different also from ResNet. There's no bypass layer. I mean, would you say your DesNet is more similar to FractalNet or to ResNet?
So yeah, it's somewhere. So right. So fractal nets basically say, well, they have some complicated. Well, I shouldn't say complicated, but at the end it ends up being complicated fractal structure where they basically have different paths to the network, and not just this one, this path and this path, but they also have, they may have another parallel layer here or something. Ultimately, what we found is fractal nets are a lot more complicated and are doing worse. So what we, in terms of the big part of the DesNet research was holding back my students and saying, don't submit yet. We want to come to the simplest, we really want to kind of boil it down to what's the simplest design that really, makes a difference, right? For us to really understand what's going on. And so I think we kind of got pretty close to that with dense nets. And I think these other approaches, they tended to make more complicated architectures that ultimately, I think, added unnecessary complications.
What are your next steps or next ideas for improving density?
Well, I can't tell you. But we are writing a paper, for ICLEA and for CVPR right now. So hopefully we can get it working. Yeah, I'll tell you in a couple of weeks. We put it in the archive.
One more question. For the dense nets, you had sort of layered dense nets. Did you try just downsampling the feature space as is instead of making these
Oh, these blocks, these connected blocks. I see. So what he's saying basically, we had these connected blocks, and we connected everything within that block, and then we had another block and connected everything within that block. And so your suggestion was instead to do?
the blocks were because of the downsampling, so you keep things in the same feature space, basically.
So one thing we did, after the paper was published, we also tried actually getting rid of the blocks and just connecting everything with everything. And when you connect something that has a larger feature map to something that has a smaller one, we just downsample in that connection. And turns out that works just as well. So that's also, that's a good idea. Yeah.
Final question, just since a lot of students here are robotics students, have you thought about connection with robotics?
Well, so one thing is now the network's a lot smaller and they'll use less energy, so you can fit them on robots. That's I think the extent.
I'm sure you'll talk more about that. So, but you will see a lot more robots here today, and let's thank Kilian again for a great talk.
Thanks.
Take your things off.
It's a great talk, Kilian.
Hi, George. Good to see you again.
That was really
Thank you.